conductive wire is thought of as having almost no resistance, it does have some resistance over miles and miles of wire. This cumulative resistance is enough to cause a voltage drop over the resistance of the wire itself.
Let's look at a mathematical example which compares the power loss of AC and DC during transmission.
Use the power formula I equals P divided by E. If a DC voltage of 100 volts were used, then when the power demand was 1,000 watts, it would require a current of 1,000 divided by 100, or 10 amps in the power line. Assume that 100 miles of power line has 10 ohms of resistance. Since the power line has 10 ohms resistance and power equals current squared times resistance, the power loss, just in the power line, would be P equals 10 amps squared times 10 ohms, or 100 times 10, which is 1,000 watts. This means that the source would have to supply 2,000 watts to get 1,000 watts to the destination.
This would be a significant waste of energy used up in the power lines in the form of heat. However, if AC is used, it can be stepped up from 100 volts to 10,000 volts AC, for example.
Now, for the same power demands as given in the previous example of 1,000 watts, the required current would be 1,000 watts divided by 10,000, or 0.1 amp. Using the same 10 ohms of resistance, the power now lost in the line is P equals 10 times 0.1 squared, which is 10 times 0.01, or a tenth of a watt lost by using AC. Now the source need only supply 1,000.1 watts to transmit 1,000 watts to its destination.
From this example, you can see the enormous amount of energy saved by using AC to transmit electrical power rather than DC. Most electrical energy generated for public use is alternating current. The production of AC relies on the relationship between magnetism and electricity. Let's see how.
In the last part, you saw that magnetism and electricity are closely linked. Using iron filings, you saw how an electric current passing through a conductor creates a magnetic field around it. This is electromagnetism. But the reverse is also true. Magnetism can induce a current flow.
But before doing a demonstration, let's consider some important safety requirements. Since the human body is able to conduct electric current, you must make sure you are properly insulated from any conductive paths. Here are some personal precautions.
Never wear jewelry or any sort of metal when working near electric current.
Always wear some form of eye protection.
There is no special clothing requirement for electronics technicians other than common sense. No loose clothing that can get caught in the moving parts of an electromechanical device, for example.
Here are some precautions for equipment. Never use frayed or cracked cords.
Only use tools that are properly insulated.
Consider all wires hot.
Remember, safety always comes first. Now let's demonstrate how magnetism can produce electricity.
This can be done by using a horseshoe magnet, which has a north and a south pole and a magnetic field between them. A length of copper wire is used as a conductor and is connected to a zero-center microammeter. Look at the meter. Notice that the pointer rests on 0 at the center of the scale. Watch what happens as the conductor is passed downward through the magnetic field. The pointer moves to the right, indicating a current flow in one direction. Now the wire is passed through the magnetic field again. This time it's passed upward, cutting the magnetic field in the opposite direction. Notice the pointer now moves to the left of center, indicating a current flow in the opposite direction.
This simple demonstration reveals the basis for the production of AC electricity. A wire cutting the magnetic field produced current in one direction. But moving the conductor back the other way through the magnetic field caused current to flow in the opposite direction.
Current flows in this circuit because the movement of the wire through the stationary magnetic field causes a voltage to be induced within the conductor.
Let's try a different approach. This time, the wire will be in a fixed position.
The magnet is passed near it in an upward direction. Notice that the meter indicates that a voltage is induced. So it doesn't matter whether the magnetic field is passed over the stationary wire or the conductor is moved through a stationary magnetic field. Both actions will induce a current to flow through the wire.
This process is called electromagnetic induction and is the principle behind the generation of AC electricity. In order for it to occur, either the conductor must move or the magnetic field must move. The voltage generated in the conductor is called an induced voltage. Using a length of insulated wire for demonstration purposes, let's look at 4 factors that affect the induced voltage.
One is the strength of the magnetic field. The stronger the magnetic field, the greater the induced voltage will be.
Another factor is the speed at which the conductor or the magnetic field is moving relative to the other. The faster the speed, the greater the induced voltage will be.
Another factor is the angle at which the magnetic field is cut. The more perpendicular the angle, the greater the induced voltage will be.
And a final factor is the length of the conductor within the magnetic field. The longer the length of the conductor moving through the magnetic field, the greater the induced voltage will be.
Stop the program and complete activity number 2. When finished, continue watching the program.